Hello everyone, so my name is Amina. I finished my PhD in machine learning years ago in University of Geneva. Then I stayed at the same group, continuing my research. So the work I'm going to present to you today is the one that we have done at the last years of my PhD with my supervisor, Alexandros, and our collaborator, Brooks Page. So he's currently at UCL now. So we have been looking at this problem of doing the inverse of molecule property prediction. So given a set of property, can we generate multiple very diverse molecule that actually exhibits such properties? So for that, since considering in the this kind of molecule data set, we have a lot of cheminformatic softwares. You can take a molecule and also as to evaluate its any property, most of the property that we consider for this work. So we formed it as a supervised problem where you have molecules and you have its property. We also consider that you have an oracle function, which is this software, can take any molecule and evaluate its property. So to learn such kind of model that can generate a molecule with specific property, we modeled it as this generative model that can model the probability distribution of the molecule given the property. So to learn that distribution, so what we did is we define a distance measure in the property space. Since we have this function that can return any molecule's properties, so for every generated molecule, we can assess its property and then check how far this property from the target. So we define a reward using this oracle for every molecule, every target, and every generated molecule. So in that case, then the model that we are interested to learn is actually a stochastic policy, which you can think like why the property is a state, and the axes are the actions, like given this property, which action should I take or which molecule should I generate? So now the problem relates to how to learn this one. So the first thing is learning this distribution by maximizing the expected reward. But since the R has this oracle function, which is a software, it's not differentiable. So what we can do is obviously the score function estimator. But as it's known, like having high variance, and in this case, what happens is we have this RNN, which model distribution, and we have to sample a lot of molecules from the RNN and send it to the software and evaluate the reward. So this makes model training really inefficient because you have to unroll the RNN. And we need really large samples because for a given Y, among the millions of molecules, you have only like a few hundred of them has that property close to that. So it was like not, at least with the resource we have, computationally not very feasible. So we thought about what we can do in this case. So if you look at what happens with the score function estimator is that it tries to sample random samples from the model, because at the beginning your model is random, and try to find those samples that could give you high reward and try to move the model that direction so that your gradient will have, your model will learn to put high mass on those samples. So we thought about, instead of searching for random direction and then figure out where to go, why not directly go there? So the idea is we rewrite this expected reward objective in terms of the expectation with respect to reward. So we subtract the norm of the reward for every Y, and we rewrite it as a distribution. So now, instead of taking expectation with respect to reward, we take the expectation with respect to the normalized reward. So here, if you optimize this, what happens is you sample those samples that give you immediately high reward, and you try to put high probability mass along this sample, so you don't have to search through a lot of samples. And this is really sample efficient. You don't have the problem of like having large variance, but only one thing you need is you need to have a distribution, the normalized distribution that you can sample. And this distribution is, it's defined on all possible molecules. So what it does is for a given Y, I will check if this molecule has property close to this Y, then it will have high probability to get sampled, otherwise no. So we don't have all possible molecules, so what we did is we reapproximate this distribution in terms of training data. So for every y, we just look at all this access in the training data and then evaluate its probability of getting samples. So if a molecule in training data has property close to this y, it has high probability, otherwise no. And with this simplification, it was really easy to train. So only difference we have now is with original normalized reward, only these normalizing factors is reduced, but it's same for every y, so it doesn't affect the training. But only side effect is that with this reward, we are able to sample any molecules, but here we restrict ourselves to the training samples. And just to check before going to the molecule if it works as a proof of concept, we tried with the small artificial data where we generate Python integer expressions. So the task is to generate a lot of expressions that evaluate to a certain value. And for that, actually, it works quite well. So for instance, here, we are able to generate a lot of expressions that evaluate to 100. And this is like generation performance because what we are interested in is conditional generation, but we want to make sure that it actually works in terms of generation. And we compare here with just really simple maximum likelihood training. Of course, we have other baseline, but we don't show it here. You can check the paper. And the conditional generation performance actually improves quite a lot for our model. So you have a small mean absolute error and more accuracy. So after proving that actually it works, so we moved to the molecule data where we tested on QM9 and the Campbell. So this is a small molecule data set. This has larger but more synthesizable. And again, first, in terms of generation performance, so it doesn't really reduce the generation performance of the baseline in both data sets. But one more thing we checked also, because we want to know if the model is really learning the underlying molecule distribution or no. So we tried this filter from Brown et al. That it actually tried to filter out the molecule that is not synthesized, not easy to synthesize, and reactive, not stable. So we give the same amount of generated molecules from our model to this, this filter, and also the same number of molecules from the Campbell test set. And we have actually quite close success rate. So we assume that the model actually learns to generate like same quality of molecules as the test data or the underlying data. And this is the sample of the molecules that the model is able to generate. So among 16, the red box one are the one that didn't pass the filter, but the rest was okay. So this is in terms of generation. So what we are interested again is conditional generation performance. So for that, we condition on 9 properties that include both continuous and discontinuous properties like atomic rings, log P, and the QED score. So we measured both in terms of the mean square error between the target that we give and then the property that we get from generated molecules, and the correlation coefficient between the both target and the property we get. So it's actually really good in both Campbell and the QM9 dataset. And also what we tested is for like if we really fix this 9 property, is the model able to generate various molecules or no? So for this, for instance, here we fixed all 9 property and we generate 10 times. So we are able to generate this boxed one are novel, unique, and never seen in training data. So it works good. Another thing is what we find out is that when you work with like small molecules like QM9, because when during training we resample the training data, this actually discourages the model to find the more various data. So we added a regularizer, the entropy term. And because it's not easy to optimize, we also give an approximation of the entropy term that you can take the gradient easily. With that, the thing is, we tested how the entropy term actually affects the model. So there is a trade-off that if you increase the entropy term, you do actually increase the novelty. So you generate more novel molecules, but you also lose in terms of the mean square error, in terms of conditional generation performance. And then we also compare with another baseline where they use very often in the text. So the idea is for a fixed property, to get more samples, they assume that for a text, if I augment a little bit, it doesn't change property, so I can sample those augmented text. But we assume this doesn't hold for the molecules, because for a molecule, if you just change one, if you do just one added distance by changing one atoms, sometimes you get totally like invalid or like different molecules. So we did a bit statistical, and then actually it was true. So until if you do 6 added distance on QM9, you get like 0 valid molecules, and your MSE also, the MSE between the original molecule and the molecule you get, the property is changed, like they have a really big difference. So we say that this kind of approach doesn't work on the data set, that when your data is very sensitive with the local change. But the model we propose, it works in this case. Another thing, so this is the previous work, but going back to the same problem of like generating molecule for a given target property. So you have actually 2 approaches. One is generating really from the scratch, and the other one is starting from a prototype molecule and modifying a little bit so that you have this new molecule with a similar structure but a different property. So we were more interested in this kind of problem, but this kind of problem you can only model with the latent variable models, because you need some kind of structural information of the original prototype molecules. So you have to have a latent variable model. So previously we tested this one. Actually, we presented the same model here, this approach, like 2020. So what we find is that the autoregressive model, which is the one that I present today, directly just modeling the px given y. It has really good generative performance, but you cannot do this kind of approach we call style transfer. Like you can take a molecule and then change the property while not staying too far away from the target. This you cannot do it because you don't have information about the structure. And with latent model, you can do it, but it has poor conditional generation performance in terms of when you do a style transfer. So this is statistics on 2 models that we have done. So LSTM, this resembles the model that I present today. The green one is the one that we done previously. So if you look at the residual of the arrow conditional generation performance, so LSTM do pretty well because it actually generates a molecule that actually matches the Y. But since it doesn't have the structural information, so if you give a prototype molecule, you cannot get any molecule that is close to that. While the VAE model, the latent variable model, it can generate actually some molecule that resembles the original prototype, but it fails in conditional generation performance. Like it has really bad performance. And so we were investigating this. Like also we checked other existing model. They also claim they do conditional generation performance generation with the VAEs. We exclude those models that do Bayesian afterwards in latent. So this is only 2. There's of course many. So of course, like those models, this one has quite good, impressive conditional generation performance. But what we find out is that because the decoder using, again, an autoregressive model with teacher forcing, so it's somehow went back to an autoregressive model. Like it can really ignore your latent and just do a px given y, because they didn't report the style transfer, so we cannot confirm with that. But at least by looking at the model that they provide and by testing them, we didn't find like it's able to do style transfer. So it's very easily that if you don't use teacher forcing, you go back to, you don't get a good performance, but if you do, you go back to our autoregressive model. So to solve these things, to combine the advantage of both worlds, so what we assume is that the VAEs work worse for style transfer because of lack of supervision, because when you take a molecule and try to modify it, you don't know what you are generating. You only can assess if the molecule has the property you give, but you don't know how it looks like. So this feedback loop is really long. So the idea is provide more supervision. So since we have this autoregressive model can actually approximate really well the conditional distribution, then we can use this one, give us supervision. So for a VAE, you can add this as a fixed distribution to see that if generated molecule from style transfer fall into this one or no. By maximizing this one, you can push the molecule. You can give supervision. And the other one is take this autoregressive model, which works well for px given y, give a z that actually has structural information, where the z you learn separately. And this hopefully will also give an autoregressive model can do both style transfer and the conditional generation performance. Conditional generation. Okay, yeah, that's it. If you have questions, yeah.